Hello everyone, my name is Dr. Afaq, and as you all know that I have started a video series on understanding my research articles, both in which I have been first author or in which I am co-author. So the idea is to understand those research articles, what work I have done so far, and creating a very easy environment for new researchers who have just started their research career to understand and comprehend those articles. Specifically, there are some confusions while reading the article, so I will try to discuss the research article as easy as possible so that everyone can understand in a simple way. So the title of the article is highly stable soft strain sensor based on glycerol potassium chloride filled sinusoidal fluidic channel for wearable and waterproof robotic applications. So let me show you first the research article. You can see over here, this is the title, and this was published in Smart Materials and Structures, that was IOP publishing. So it's a close access, we didn't pay any thing to the journal. So this is the DOI for this journal, and I will also add the link for this paper in the description so that anyone who is interested can read this article. And these are the authors, and that was published back in 2020. So we submitted that on 18th of September 2019, and it was accepted on 4th of November 2019. I think it took 2 months hardly, but after that obviously it took some time to get it published, means the issue number and volume number. So let's jump to the abstract. So you can see over here that this is highly stretchable and linear liquid type, or you may call fluidic type strain sensor. So it's a flexible strain sensor. So if it is flexible, stretchable, that means it can be used for wearable application, and that's what we targeted. And that was also used for robotic applications, because my core field was robotics, and especially soft robotics. So in order to make robust robots, you have to add sensors, and if the robots are soft, means flexible, so they also require the flexible strain sensor. So that's what we developed. And another thing was that we wanted to use that material which was not only sensitive, but it should be biocompatible, because we are targeting wearable robotics and wearable electronics application. So for that you need to develop that device which has eco-friendly nature, and that was our target, and we got success in it. And as far as some quantitative features are concerned, and you can see over here that the hysteresis was only limited to 4.23%, which is quite good as far as fluidic type strain sensors are concerned. And if you stretch and release this sensor up to 5 hertz of speed, then this sensor could easily follow that applied force. So that was quite good, and that made this a robust candidate for robotics applications. And then you can see over here that the stretching, I mean the maximum stretching that you could do was 100%. That was also a promising feature, and the gauge factor was 2.7. The people who are already familiarized with these kind of sensor, they may say that this gauge factor is quite less. Yes, you are right. If you talk about the strain sensor which are developed using nanomaterial or piezoelectric or piezoresistive approaches, so obviously this is quite less, but as far as liquid type is concerned, this value is still significant. And we tested this device up to 8,000 cycles at 25% strain. So this also confirmed that the sensor can be a good candidate for commercialization, and it has very good reproducibility. And the optimization of the design was also done using COMSOL 5.4, and that was using FEA tools. And then later on we used the sensor in the applications such as wearable monitoring and then robotics. So let's jump to the presentation, that will also give you a very good idea. So research motivation, obviously when you see the human body, there are a lot of parameters that are really important to be monitored, such as breath rate, joints movement, pulse rate, fingers bending. So these all things, they play a pivotal role in understanding the human physiology. And for that, obviously you need sensors. Like if you want to measure or monitor the environmental factors, you need humidity, temperature, gas, light, radiation particles, etc. These are the sensors, and the other sensors you can see over here. And as far as performance is required, obviously, day by day researchers, they introduce different devices, and the goal of those devices is obviously to improve the performance. And what are the basic requirements? Obviously it should be requiring less money to be fabricated, and the fabrication process should be reproducible and very easy. It should be very highly sensitive. It should be capable to sense wider range of the quantity. Like if you have temperature sensor, and if that sensor is just sensing the range of 20 degrees centigrade to 50 degrees centigrade, obviously that is not commercializable. That won't be a better choice. So we will prefer that sensor which is having wider range. It should be robust, it should be accurate, and the response and recovery time should be very fast. It must be stable and highly selective, and obviously application specific requirements. One thing is quite important, that not all parameters can be achieved by a single device that you have developed. That's for sure, but you have to target that which application you are targeting, and that application requires what kind of parameters to be promising, to be very good. And in that case you fabricate your device. And then the research goals, obviously that is to improve performance, fabrication through printed electronics approaches, and of course reducing the cost of fabrication. So that was a research motivation, and in this research article we are focusing on the strain sensor. So when your body joints, they are moving, they are developing some motion, we must study them, and by critically monitoring them, we can jump to a specific conclusion that what kind of problem a human is facing, or what kind of issues that human might have in the future, like chronic diseases are there. So this is what we are motivated by. And as far as fabrication process is concerned, this was a fabrication process. It was completely reproducible method, and we use EcoFlex, which was skin like material, and the sensing material that we inserted using this stepper motor controlled fluidic system, that was glycerol and potassium chloride. So potassium chloride added the conductivity in the glycerol, and overall you can see that this was also a simulation, and this was a simulation result. So material method in the humidity sensor, I will give the link in the description. That this is the last video that I made, and that was for monitoring the human breathing. But in this article we are focusing on the sensor one that we developed, and that was glycerol and potassium chloride. In the next video I will discuss about P.PSS and multi-valve CNTs based strain sensor, and it has better features than the first one. But for now we are just targeting this research article. This fabrication process is almost same like in this article that I haven't discussed. So in the next video I will discuss, but this is completely same. And in the research article that you will be studying, you will see that we have also cited the previous article that the fabrication process is almost same. So here what we did, we 3D printed a mold in which we added sinusoidal channel, and we poured EcoFlex, that is highly elastic, highly flexible material. And once it was cured, you would see that you will peel out that, and you will see this pattern being made. So that would be engraved channel. And what we did, the second membrane, of course you have to completely close this, otherwise the liquid, conductive liquid that you will add over here, that will be coming out, and your sensor won't be working. So in that case you have to add another membrane that would be pasted over here, and we use blade coating process to make ultra thin membrane, so that should not disturb or affect the overall flexibility and stretchability of our sensor. And this was the membrane that we made using this process, and that is half cured. That means we didn't let it completely be cured. We, for example, if it is getting cured in 6 hours, so we just gave it 3 hours, and after that we put this membrane and this material that we made using this step exactly perpendicular, so that we can attach together. So this is the final product. And after that, what we did, we added the conductive liquid. Don't look into this please, because we added this material, glycerol and KCl. Potassium chloride is actually a salt, and that increased the conductivity of glycerol. And glycerol was a biocompatible material, and its viscosity was not that much high and not so low that could create some noise in the sensor. So that is a fabrication process. And then analysis, of course, we had the universal testing machine, and we tested this device. This is the working principle. So this is the fabrication process. If you remember, I told that the same fabrication process was used for the next paper. So you can also see here how we did it. And this is the working principle, that KCl ions in the glycerol, they are created across the channel, a sinusoidal channel. And this mechanism tells you that why we opted the sinusoidal channel, because the stress was non-linear across the channel, and that put some non-linear stress over the liquid that we added, a conductive liquid, that resulted in the increased conductivity and increased sensitivity. So these are some equations. This is the basic gas factor equation. You can look into it. Degree of hysteresis, which is also called the memory effect. So that's quite straightforward, you can see. And these are some results. If I just zoom it, you will see here that this is the loading and unloading. So we stretched it from 0% to 100%, and then we released it from 100% to 0%. So ideally this should be exactly on top of it, means degree of hysteresis should be 0, but obviously practically sometime your liquid inside the channel it takes to go back to its original position, and that's what the hysteresis is all about. And 4.23%, it was quite acceptable. We stretched our device on different frequencies, means on different speeds. So you can see from 0.5 hertz to 5 hertz, your results are quite consistent, and there is less deviation among these different experiments. And then we also proved that our sensor is immune to temperature, and we checked it from 20 degrees centigrade to 40 degrees centigrade. And why we selected this range? Because you can see that the body temperature of a human would be more likely in that range, and we can see that very insignificant effect is there on the sensor's performance at different temperature ranges. Then we also checked our sensor because we highlighted that the sensor can be used for waterproof applications. So at 100% humidity in the chamber, we placed a sensor, and you can see that its resistance is almost constant, that is about 1.15 or 1.25 mega ohm. And similarly, the gauge factor, you can see that as you are increasing the strain, means stretching, the gauge factor is increasing. And the stability is, you can clearly see that for almost 15 minutes we kept on stretching the sensor up to 50% using that universal testing machine, and you can see that the response is quite consistent. There is very minute level of noise that a sensor is producing, and that's again quite acceptable. And similarly, that is the comparison table, and I have already made the video on this, that why it's important to add the comparison table. I will also add the link of this video in the description, and hope you will like that video as well. So as far as reproducibility is concerned, cyclic response obviously is necessary to be provided, and we tested the sensor up to 8,000 cycles, and these are some pictures. And then obviously I told that optimization was done in the very beginning using COMSOL software. So previously the straight channel sensors were developed, and we introduced this new design, and you can see that there is a huge difference in the distribution of surface pressure, as if we consider, if we compare its counterpart, that is straight channel. And similarly, total displacement was also quite promising if we talk about our channel as compared to straight channel. Anyways, so then we use this in applications like finger bending, robotics, that there was a frog limb, and we used it for 3 different angles, and you can see the significant differences there among different angles. And then water drinking behavior or swallowing behavior of a human subject, we also provided the result, and again bending, fast bending, slow bending, and then statistical analysis about 3 samples. And of course, we use this as a feedback sensor for a frog robot limb, and we put that sensor which was placed on the frog's limb inside water up to 30 minutes, and the result was quite consistent. The video is also provided with this research article. If anyone is interested, they can find it on journal's website. So further results, response time, that was 0.8 seconds, and recovery time was 0.9 seconds. This was again a stability testing that we used multiple cycle for each stretching, like 25%, 50%, 80%, 100%, and then the distribution of material like 6 gram of KCl and 10 ml of glycerol, and if you keep on decreasing, you will see the change in the response. And this was a linearity testing. The COD was 0.986. It was again a good parameter which was acceptable by the journal. And then this one, the elbow movement, the result is given, and this is knee joint if you are doing squats. So you can see a huge change of response while you are doing squats or jumping. So easily you can recognize 2 different activities are human subject. These are some results that if you are applying stretching force at speed of 2 hertz, see the response. And then we have 10 hertz. Again 10 hertz, there is little variation, but that would be manageable. But to be on the safe side, what we did, we reported or claimed in the journal that is 5 hertz. And this is the statistical analysis, that what is the standard deviation among 3 samples that we provided, and you can see the references. And I hope this video would be helpful for those researchers who are interested in this flexible electronics. If you have got any questions, you are more than welcome to discuss with me. We can collaborate, we can discuss further, and I think it would be very nice if you take this to a next level. There are many other shortcomings in the sensor which can be improved over the period of time, and I hope someone will do that. Thank you so much.